Hello viewers. So in today's video we are going to talk about everything from the high level perspective of IS-IS. So we are going to see that what are the packet formats that is exchanged while forming a IS-IS membership, and we are going to see what are the major changes that has been occurred in the IS-IS from the first RFC to the latest one. So yeah, that's it. We'll see all of this in today's video. So without wasting much time, let's get started. So just to give you an overview, we had already covered the first session on the IS-IS where we had covered the introduction part and the basics parts. So where we will quickly go through the previous slides. So this was the introduction. Then we had a high level overview. So here are some of the whys and why nots to use IS-IS. Then there are certain naming conventions that we use. Then this is the system ID that we use in the IS-IS addressing scheme, so that we had an introduction about this one. Then what are the different routing tables that we use and what are the different router types. So this was the previous session. If you are not aware about the first session, then I might have a link over here in the I button. Please go through that link and you will be get to know about the basics of IS-IS. So with that discussion in the mind, let's get started with today's discussion, where we will start our discussion by the IS-IS operations. So first we will have a brief of IS-IS routing, how it occurs in the very high level introduction of the procedure or the operations of IS-IS. So first we have seen this is the addressing scheme for the IS-IS protocol, right? So first part, this much of parts which involves this 1 byte, 2 byte and 3 byte. So this 3 bytes is used as an area ID. Then this 6 bytes, the next 6 bytes are used as an system ID, and the last byte is used as an selector. So you can consider this as an individual system ID that is used for the area 1. If it is for area 2, we can see that 49.0002 is used over here, and if it is for area 3, we can see that 49.0003 used over here, right? Then we have something called system ID, which is unique in the area. So this system ID 1111.1111.1111 can have can be there in different areas, but it cannot be again in the same area. So this let's say for this device, we cannot assign this system ID again because those are in the same area and they will collide. So system ID can be repeated for different areas, but it cannot repeat in the same area. Now if you are aware about the level of routers, the that we had in cover in the last session. So this is the level 1 router who is connected to an system, and the another router in the same area. This is the level 1 and 2 router who is connected to any level 1 router in the same area, or end in the router who is connected in the different area. So that is level 1 and 2 router. Then level 2 router who is the individual or the only router in the area, so that is level 2 router. Then this is again level 1 and 2 router, and this is level 1 router. As per the discussion, level 1 router who will only have this level 1 LSDB, who is which is nothing but the mapping of system ID with the port number. Then level 1 and 2 router will have level 1 LSDB and level 2 LSDB. So level 2 LSDB is nothing but the area ID mapped with the port identification. So that level 1 and 2 router will have both of these LSDBs, and level 2 router will only have level 2 LSDB. So that's the difference, or that's the brief of IS-IS routing. Now let's consider that this device needs to communicate to this device. Then we have this kind of table which is mapped with the system ID and the port, right? So let's say if we want to communicate to this end system, we will have a mapping of how to reach to this area from this router. Since level 1 router don't have this mapping of area with the port, then level 1 and 2 routers responsibility is to add and default route to this level 1 router, right? So that we have seen already in the previous video. So what will happen is there will be a default route which is having system ID 0000, all zeros, and with the port mapped to this interface over here. So whenever let's say we want to communicate to area 3, we will use that default route which is over here in the system ID and which is mapped to the port number which is nothing but this port number over here, right? So let's say a packet goes over comes to level 1 router over here, then it goes to over here. Now this level 1 and 2 router will have mapping level 2 LSTP, which is nothing but the mapping of area with the port number. Since it has this LSTP, level 2 LSTP, it will have area 3 ID over here which is mapped to port which is connected over here with the with this level 2 router that is over here, right? So there will be a mapping of level area 3 with the port which is over here. Now packet comes to level 1 and 2 router, which will be sent over to this level 2 router. Now similarly this level 2 router will also have a mapping of area 3 with the port number over here, because we can use this port number, this port, to reach to area 3, right? So packet will come to this level 1 and 2 router. Now again, this level 1 and 2 router will have a mapping that, let's say, if you want to communicate to this device, we can go via this link. And similarly, when the packet will reach over here, it will have a system ID mapped to this port over here, and we can have a successful communication like that. So this is the overall idea of IS-IS protocol. That's how that is the explanation of how this LSTBs are used, and how this level 1 level of different level of router works in the brief or high level perspective. Now this is the traditional state transition diagram for any of the IS-IS neighborship that occurs. So first, when we don't have any IS-IS neighborship configuration command on the devices, that's when the IS-IS will be in the down state. As soon as we initialize certain neighbors, we configure certain IS-IS process, there will be a initializing state, and then let's say we will have an IS to IS hello exchanged. So let's say these two devices are exchanging the IS to IS hello, so they will both exchange each other's router's ID, and the state transition will go from initializing to up, and then there will be certain LSP exchange and something like that, and that's how they will synchronize LSDB. So this is nothing but the straightforward explanation of state transition diagram that happens between any two IS-IS neighborship that occurs. Now let's get to know about certain things in the IS-IS history, right? So it is good to know about history of any of the protocol, but for the IS-IS it's a very long list. So the very first of the RFCs that has been written for the IS-IS, that was in the 1990 year, and the RFC number is 10598, or it is not an RFC, it is ISO IEC documentation that you can go through and search over the internet, right? And then we have several enhancements written over here up to 2021. So the latest RFC was RFC 9356. So you can see all of this key exchange and RFC numbers and the years that has been marked for the IS-IS enhancement. Now we cannot go through each of this enhancement because the list is very long, but I can give you a brief description of what are the major changes that has been occurred, right? So the traffic engineering support that has been included, or as part of RFC 5305. Then we have a multi-topology routing enhancement that has been included in the RFC 5120. Prefix attributes that has been included in the 7794, similar to BGP path attributes. Then segment routing support has been included in the RFC 8667, and lastly the IPv6 routing support has been included in the 5308. So these are the major enhancements, and these are the major RFC numbers that you can go through if you want to have a brief overview of IS-IS enhancement and the history. And yeah, that's it for the history part. Now we can go through all the packet formats, and this is very important part from now. So pay attention from the first introduction packet format, which is nothing but the common format of IS-IS packets. So this is a common format of any of the IS-IS packet that is exchanged while forming a neighborship, or while exchanging the LSDBs or synchronizing the LSDBs between any of two IS-IS neighbors, right? So this is the common format of IS-IS packet, where this PDU specific header, so this part may be vary and this part may be vary. The rest of this part from this intra-domain routing protocol discriminator to maximum area address, that will remain same in any or each of the IS-IS packet that is exchanged to form a neighborship or to exchange the database, right? So first, this field interdomain routing protocol discriminator, that is in discriminator for IS-IS protocol. So this field will let the device know that this specific packet is for IS-IS, and the value is generally kept 83 in the hexadecimal over here. And this length, as you can see, this is nothing but the 1 byte. So that means this much of part will contain 8 bits, right? So that you can have an idea about how the packet is formed and what is the length of the packet, right? And then we have something called length indicator. So this part will have a length indicator for the common header plus the specific header length. So this is nothing but the length indicator for the entire packet, right? So that you can note over here. Then this is the version protocol ID. So usually it is set to 1 because IS-IS version is 1, or it can be set to any other value specific to the what IS-IS version is being used. Then this is the ID length. So ID length, it is nothing but the IS-IS addressing scheme. So the length of an SAP address. So an SAP address, as you might know, area ID, system ID, and the N selector that we have seen in this video also, in the last video also, right? So if it is set to 0, the length of both system ID and area ID is equal to 6 bytes. If it is all ones, that means 255, both are empty. So that's the way of interpretation of ID length. Then these are the reserved bits. All these reserved bits are set to 1, and this rest of this bit is PDU bit. So rest of the 5 bits, because this entire is field is 1 byte, and these 3 are reserved bits. So left over 5 bits are used for PDU type, and PDU type indicates what PDU this IS-IS is carrying, right? So this PDU specific header. So this part, how to interpret this PDU, that is mentioned over here in the PDU type. So that is the 5-bit value. And what are the values that can be used over here, that we will see in the next slide, right? So version, that means IS-IS version number set to 1. Reserved, so all the bits are again set to 1. This is the reserved 1 byte. Maximum area address, so that this field it supports, or it means that what are the maximum number of supported areas that we can use. If it is set to 0, the IS-IS process that the device is running, it will support maximum of 3 areas. Else, what is the value of this field? It is the value of maximum area supported. So generally it is ranged from 0 to 127. And this is PDU specific header. So this part, there are several packets, or there are several headers that can be put over here, so that we will see in the next slide. So now about this one, PDU type. So let's see that. So in the previous slide we have seen the PDU type, that is the 5-bit value. So what are the PDU types that we can use? So these are the values that we can use with in place of that 5 bits over here. So if it is 15, so the PDU type is level 1 len IS-IS hello PDU, and the abbreviation or the short form of this is L1 len IIH. So that's how these values are being kept, and that's how these values are being interpreted. So you can have the snapshot of this table to see what are the PDUs that will be carried over here in this PDU specific header. Now what is CLV or TLV? So code length value or time length value. So as you can see, this field over here, variable length field, so that is nothing but this is something called code length values. So there are several values that can be put over here. So these are like CLV codes that you can see over here, right? So if it is something like 1, then the length of or the name of this parameter that will be sent over here as a value, that is area address. And PDU type, so what are the PDU types that this CLV can carry, or these are the PDU types that can carry this CLV. So that's how this entire table is interpreted, and the code value means what is the value that is carrying over here, right? And the length value indicate what is the length of this particular value field over here. So that's how the CLV is being carried in any of the packet that we will see in the IS-IS. So that is the common format of IS-IS packet. Now the second packet is that is the first IS-IS complete hello packet, right? So this is the complete hello packet. So this PDU common header that we have seen in the earlier slide, and what is the interpretation of each field. Now this is the hello packet. So after this entire common header, we will have something called these many fields. before this variable length fields. So this is something called hello packet field. So all the fields that will be only carried in the hello packet. So the purpose of this hello packet is to maintain and build the neighborship between the nodes. And there are several hello packets, so such as level 1 lane IIH, level 2 lane IIH, and the P2P IIH. So these are the types of hello packets that we can have in the IS-IS. And how they specify this type of hello is what is the type of hello packet is this. So let's see in the next slide. Now this is the specific hello packet. So we have removed the common header that comes before this PDU specific header, and this is the hello packet, and this is the variable length field. So this reserve or the circuit type, this field, as you can see, so 6 most significant bit is equals to reserve. Sorry, 6 most significant bits is equal to reserve, and the last 2 bit indicate the router type. So if it is 0 1, that means level 1 router. If it is 1 0, that means it is level 2 router, and if it is 1 1, that means it is level 1 and 2 router. So that's how this circuit type value is indicated. Now the source ID is nothing but the addressing scheme that is used by the IS-IS. So this will be nothing but the system ID of a router that sends the IS-IS hello packet. So the length of this field is ID length, right? Then hold timer. So if no hello packet is received within this time, so whatever the time is mentioned and exchanged in this packet from this field, so at the end of this time the neighborship is terminated if there are no hello received from the neighbor. So that is the nothing but the hold timer. Then we have something called PDU length. So that is the total length of this specific PDU, right? Then we have something called reserved bit, and the last 7 bits are for priority. So the priority of this hello packet, that is in the exchange the hello packet. So the importance of this priority field is to elect the DIS. So DI is nothing but the designated intermediate system. So larger the priority value, higher the priority. So that means whenever we want to select the elect the designated intermediate system, this priority value is used to elect the devices. Now how this DIS is important, that we will see in the next slide. But for this rest of the fields, you can see that lane ID is nothing but the DIS system ID plus 1 byte pseudo, so 1 byte random value, which is used to carry the broadcast network or not in the point-to-point network. So whenever we elect DIS, so we are in the broadcast network. In that specific scenario, the lane ID is nothing but the value that is being used to carry the packets. Now the local circuit ID, that is only will be used, and that is 1 byte value. So that will only be used when we are carrying the P2P network. So yeah, that's how the hello packet is being structured. Now let's look at the what is the importance of priority field that is exchanged over here. So you might have seen this diagram when we were learning the OSPF protocol, right? So let's say for OSPF we have already learned that there is a concept of designated router and a backup designated router. And when we have area 0, all of these devices in the area 0, and all of those are connected to forming a neighborship, then those devices are connected in the broadcast network, that we can say. Not all the devices are not connected in the point-to-point network. So in that case, we will elect something called designated router that will exchange the routing information in this particular area. And if this device is failed, we have something called backup designated router. So this device will take care of the routing updates when we will run into scenario where DR is failed. So why we use this designated router and backup designated router? Because we want to reduce the number of routing exchange that might happen when, let's say, 2 devices will send the duplicate routing information in the entire area. So that's why we have something called the DR and BDR. So similarly, we have something called DIS and BDIS. So designated intermediate system in the and the backup designated intermediate system. So that is the same concept what we have seen in the OSPF for DR and BDR. And you can also for the illustration purpose, you can also consider that this is the area 49 .0.0.49.0001. So that's how this DIS and BDIS is important when we consider or talk about this priority field over here in the hello packet. Now these are the CLVs that might be exchanged. So over here in the variable length fields, so what are the CLVs that can be exchanged over here? So remember, we have seen this table earlier. So all the PDU types that are mentioned as IIH, so those all fields, those all CLVs can be carried in this packet over here as part of variable length field. So that's how this table is useful. So you can mark all of these fields, all of these PDU fields where it says IIH. So all these CLVs can be exchanged with this hello packet. Now the third packet type is IS-IS complete link state PDU. So link state PDUs, so they are used to exchange link state information. That means what are the links that are reachable via particular device. So that is communicated through this link state PDUs, and they are classified into two categories. So first is level 1 LSP that will be exchanged from the level 1 router, and level 2 LSP that will be exchanged from the level 2 router. And level 1 and 2 router can exchange both of the categories of LSPs because as the name suggests, they are level 1 and 2 router. So this is the PDU common header that is common for all the PDU types that we have seen in the earlier slides, and this is the PDU specific header which is called link state PDU, right? So, and at last we have something called variable length CLP. So let's remove the PDU header and focus on the link state PDU. So this is the link state PDU, and as you can see, all the fields, length of all the fields are mentioned over here. And let's get to know about the field importance. So the PDU length. So as the name suggests, this PDU length value that indicates what is the length of this entire PDU. And then we have something called remaining lifetime. So that is nothing but the, as the name suggests, remaining lifetime of the LSPs in the seconds. And then we have something called LSP ID. So LSP ID is nothing but the system ID plus 1 byte pseudo ID plus 1 byte fragment ID that you can see over here, right? So that is used to uniquely identify this link state PDU. Then we have something called sequence number. So sequence number, which means what is the sequence number of this particular LSP that is being exchanged. There might be a multiple sequence number or multiple LSPs that might that might be reached in order in some particular neighbor. So that's why we use the sequence number. Then we have also have something called checksum to verify that whether we have received the correct packet, because this checksum is used to detect the error in the packet. Then we have something called 4 bits ATT value, and before that we have something called 1 bit P value and 1 bit value where this P bit indicate that whether the node support automatic partition repair from the L2 LSPs, so level 2 LSPs. So most of the implementation of IS-IS that we have today, whether you talk about Cisco, Arista or Juniper, most of them don't support this system because it is not implemented. I don't know for what reason. There might be certain reason why they ignore this value, but you can search or research on the Google about this automation partition repair. And then we have something called 4 bits ATT value. So ATT means this is the attachment bits. So this indicates that the originating router is connected to other areas. Then we have something called overload bit. So this is set. If this overload bit is set, then that means LSPs are not used for the SPF calculation. So overload bit means that whatever the device that is sending these LSPs, that is overloaded. So that's why all of the PDUs, all of the links that are exchanged in these PDUs, they are not used for the shortest path calculations. And simply they will be there in the database, but they will not be included for the SPF calculations, right? Then we have something called IS type. So this is the 2 bits value, and this indicates the type of router that generates the LSP. So that's the entire link state PDU. So again, let's get to know about what are the CLVs that can be exchanged over here as part of the variable length fields for the link state PDUs packet format, right? So wherever you see LSP in this PDU type field over here, those all the values, those all the CLVs can be exchanged over here in the as part of variable length field for the link state PDU packet, right? So you can see and mark all those fields value over here, and that's the importance of this table. Again and again I'm saying this, so you can take a snapshot of this table because this table is very important if you want to understand the packet formats, right? Now the second last part of the IS-IS packet format, that is complete CSNP packet. So CSNP means complete sequence number packet. So they describe all the LSPs in the LSTB. So as the name suggests, CS complete sequence number packet, that means that all the LSPs in the LSTB are exchanged via this type of packet format, and they are generally used to synchronize the LSTB because as the name suggests, complete sequence number packet, right? So you can guess what will be the working of this packet format. Then this is on the broadcast network, only DIS sends this packet at certain interval, and the default interval for that is 10 seconds. So every 10 seconds this CNNP packet will be exchanged to all the neighbors that are in the same area. Then on P2P, each device is send this packet to each other. So that's the difference between broadcast and P2P network, and that's the use of this CNNP packet. Now let's remove this PDU common header and focus on this PDU specific header. So this is the PDU specific header. So as you can see, all the length of the fields are indicated over here. Now PDU length, as the name suggests, so the total length of PDU is indicated over here in the first field. Then we have something called source ID. So that is nothing but the system ID of the sender router for this CNNP packet. Then we have something called start LSP ID and the end LSP ID. So that means the first LSP in the CSNP and the last LSP in the CSNP. So that indicates what will be the length of the LSP entries that we will be exchanging. And generally, if entire LSP is exchanged, then the start LSP ID will be 0000, all zeros, and the end LSP ID, that will be all ones. Now that is nothing but the CSNP packet. Now we are about to end this packet format discussion with this last packet format of the IS-IS, which is something called complete PSNP packet. So PSNP, full form of PSNP means partial sequence number packet. So they describe some LSPs in LSTB. So as the name suggests, partial sequence number packet, and they are used to synchronize and maintain LSTBs. Again, this will exchange the partial sequence number of the LSPs. That means not all the LSPs that might be exchanged, and these are also used for the acknowledgement of the CSNP packets or the LSPs that might have exchanged in the CSNP, right? And a PSNP lists only the sequence number of the recently received LSPs, and it can acknowledge multiple LSPs, and it can also ask for the multiple LSPs. So that's how PSNP packet is used, and these are the responsibilities. Now let's ignore this PDU common header and let's focus on this PSNP packet. The length of each of the fields are described over here. PDU length, that means total length of PDU, and the source ID, that means system ID of a router that sends the PSNP packet. Now that's nothing but the packet format of PSNP. So I hope that you have got the idea about IS-IS packet formats history and how IS-IS works in the backend. I know that this video is very long, but I need to make this because we need to keep our discussion very clean. And yeah, that's it for this video. If you have any doubts regarding the packet formats in the IS-IS or how the IS-IS membership is formed, you can ask me in the comment section below, and I'll hope to respond those comments very soon. And we'll meet in the next video. Till then, keep learning and keep exploring.